All right, now we are going to look at this question 17, whereby iodine is going to react with propanone under acidic condition. So the overall equation is given. So in this study, what we are seeing is that we have a mixture of propanone and HCl were placed in a flask. Okay, then 10 cm cube of iodine was added to it. So we will see that the propanone and the iodine will be reacting in the acidic medium. So the timing began immediately after mixing, and then 10 cm cube of samples were taken at 10 minutes intervals, etc. And then you add in some hydrogen carbonate to the sample, and the unreacted iodine was then titrated. So let's look at what's happening. So we are seeing that they are removing samples at regular time interval because we want to monitor the progress of the reaction. Right? Now, then there's a funny thing. Why are they adding this sodium hydrogen carbonate to the sample? So the reason why they're adding the sodium hydrogen carbonate solution to the sample is to remove the acid. So remember right at the start, there was HCl added, and that is in a way a catalyst. It catalyzes the reaction under acidic condition. So the sodium hydrogen carbonate was added to remove the HCl catalyst. So it's actually added with the intention to quench the reaction. Okay, it's a quenching agent to quench the reaction. All right, so after that, we take our sample and then we're going to look at the unreacted iodine. So iodine here is a reactant. So we will expect that with time, there should be lesser and lesser iodine. So that's what we are seeing in the graph. It's a decreasing graph, right? Okay, so next. So if you look carefully at the amount, let me highlight to you where's the amount. If we look at the amount of the propanone, it's not the 20 cm cube that I'm asking you to look at. I'm asking you to look at the concentration. So we have 20 cm cube of 1 mole per dm cube propanone, and then we have 10 cm cube of 1 mole per dm cube HCl. But when it comes to the iodine that we are putting in, it's not 1 mole. It is only 0.1 mole per dm cube. So it's like 10 times more diluted. So the purpose of it is to make sure that propanone and HCl was added in excess. So therefore, this part of the question is asking why propanone HCl is used in such large excess, and what's the purpose of adding sodium hydrogen carbonate. So the purpose of adding propanone and HCl in such a large excess here, because what we are doing is we are monitoring how the iodine changes with time. So we are keeping them in large excess so that the concentration will remain relatively constant. And what happens when the concentrations remain relatively constant? You will find that it becomes like a zero order reaction. Because you have a large excess, there's no change in concentration. The only thing that is changing concentration here is iodine as it occurs with time. So the large excess of the propanone and HCl ensures that the two reagents are in large excess, giving rise to a constant concentration, and therefore the reaction is likely to be zero order with respect to the propanone and the HCl. Okay, it's not a real zero order, so we actually created that zero order, so it's called a pseudo zero order. Okay, and the purpose of adding sodium hydrogen carbonate, so we already mentioned why we add sodium hydrogen carbonate. Is likely to neutralize the acid, is to remove the acid, and that means in this case, the acid is a catalyst, okay? So it removes the acid catalyst. So you can say that by removing the acid catalyst, it actually helps to quench the reaction. Okay, done. So this first part is done. Okay, next we are going to look at the order of reaction with respect to iodine. So what we are having on the graph is not an iodine graph, but the amount of thiosulfate. So thiosulfate amount is actually proportional to iodine. If there are more iodine, then you need more thiosulfate. And therefore, the trend line for the thiosulfate reflects the same trend line for the iodine. And what type of trend line are we seeing here? We are seeing a straight line. A straight line. So in this concentration time graph, the gradient of this graph is d con dt. And d con dt is a rate. So the gradient is the rate of reaction. And what do we see? The gradient at 10 is how much? The gradient at 30 is how much? The gradient at 20 is how much? And you'll find that it's the same because it's a straight line. So we are seeing something like this. There is a straight line. That means constant gradient. And gradient is the rate, so we are expecting a constant rate. So that means, right, in this reaction, despite the changes in the iodine volume, iodine amount, concentration, the rate is constant. Despite changes in the iodine concentration with time, the rate is constant. So what does that tell us about the order of reaction with respect to iodine? It's going to be a zero order. Okay, because the concentration changes linearly with time. Which shows us that the rate of reaction is unchanged as the concentration of iodine changes. Okay. All right. So next one that we're going to look at, part C. If the initial concentration of iodine were doubled, what would be the effect? So you remember your original iodine concentration was 0.1. So what will happen if you use 0.2? So before we say, oh, it will speed up the rate of reaction, it will decrease the rate of reaction, we look at the order. We deduced the order just now, and we deduced that the order was zero order, right? Zero order. So that means the rate is not going to be affected by the concentration. So what will be the effect on the gradient? There should be no effect because the gradient is the rate and the iodine concentration has no effect on rate. Okay? Next. The same reaction was repeated, but HCl was replaced by sulfuric acid of the same concentration. The rate of experiment repeated is now twice. So they are telling you, oh, now the rate is double after we just replace our HCl with sulfuric acid. What deduction can you make? So if you look at HCl and you look at H2SO4, right? So 0.1, sorry, it's not 0.1, it was 1.0 m of HCl will have 1.0 m of H plus. But, so you go back to here, it's 1.0. Okay, but for sulfuric acid, if you have 1.0 m of sulfuric acid, you are actually having 2 m H plus. So the effect of the change here is that the H plus actually doubles from 1.0 to 2.0 by changing the acid. So we are seeing the concentration of H plus double. So concentration of H plus doubles, right? The concentration of H plus doubles. So the rate is now twice. So what does it tell us? So when the concentration doubles, rate also doubles. So it is a first order reaction. So it's telling us it's first order. So our answer for part D is first order with respect to H plus. Because sulfuric acid is diprotic. So by changing the acid, with the same acid concentration, the concentration of H plus is doubled. So rate of reaction also happens to double, and therefore it must be first order. Okay, next part E. Several experiments were repeated with varying concentration of iodine and HCl. So while keeping the concentrations of other reactants the same, sketch the likely graph of rate versus iodine, rate versus H plus. So instead of a concentration time graph, we are now going to plot a rate time graph. One will be rate against iodine. Another one, it will be rate against H plus. Okay, so let's write out our rate equation if you still remember. So our deduction just now was that the order with reaction was zero order with respect to iodine. So we will be writing rate equals to Ki to 0, right? Anything to the power of 0 is 1, so you will be writing rate equals to K. Then rate equals to K, so we will plot a graph that is like this, where rate is equals to K. Okay, now the next one for H plus is we reduce it to be first order reaction. So rate will be equals to KH plus first order, right? So when we are plotting our graph, it looks exactly like Y. Our y-axis is rate, so Y equals K is a constant because it's a rate constant, and then H plus is our X. So it looks like a Y equals to MX graph. So we will sketch a straight line passing through the origin, Y equals to MX graph. Okay, so these are the two graphs. Okay, next part. In a separate experiment, it's found that the reaction is first order with respect to propanol. So now write down the rate equation for the whole reaction. So our deduction was iodine was 0 order, H plus first order, and now they're telling you propanol is first order. So the rate equation will be rate equals to K, H plus 1. Propanol. Okay, we don't spell out propanol, so what we will do is we will copy the formula here, CH3COCH3. Okay, so we will replace this with the symbol CH3COCH3 to the power 1. And that will be the rate equation. Okay, that's for this question.